Right now, as you listen to this, something unprecedented is unfolding in our cosmic neighborhood. On July 1st, 2025, a routine automated sky survey captured something extraordinary disguised as an unremarkable dot of light. The ATLAS telescope array in Chile had photographed thousands of such objects before, but this particular discovery would soon rewrite our understanding of what travels between the stars. This video examines publicly available research and reports for educational purposes. Interpretations are attributed to their sources. Preliminary or early findings are labelled as such until peer-reviewed. No extraordinary claims are asserted without evidence. What makes an object truly interstellar isn't simply its origin beyond our solar system. It's the mathematical certainty that it can never be gravitationally bound to our sun's orbit. The object we now know as 3I/ATLAS follows what astronomers call a hyperbolic trajectory, a path so energetic that once it completes its swing around our star, it will continue outward forever, never to return. The designation itself tells a story. The I stands for interstellar, while the number 3 indicates this is only the third such object confirmed in human history. Its predecessors, 1I/Oumuamua in 2017 and 2I/Borisov in 2019, each surprised astronomers with unique characteristics that defied easy categorization. Now 3I/ATLAS continues this pattern of interstellar unpredictability, but with features that dwarf anything we've seen before. The initial discovery process reveals just how extraordinary these cosmic wanderers truly are. When 3I/ATLAS first appeared in the ATLAS database, it seemed no different from countless other minor bodies catalogued daily by automated surveys. But as recovery images emerged, earlier photographs that showed the object before its official discovery, astronomers realized they were dealing with something that had been lurking in their data for weeks. The object's speed immediately set it apart. Currently racing through space at approximately 137,000 miles per hour, 3I/ATLAS moves at velocities that dwarf anything naturally occurring within our solar system's gravitational embrace. For perspective, Earth maintains its stable orbit around the Sun at roughly 67,000 miles per hour. This interstellar visitor carries more than twice that kinetic energy, accumulated during millions of years of travel through the galaxy under the influence of distant stellar gravitational fields. But velocity was only the beginning of the mysteries. As larger telescopes turned toward this new interstellar visitor, they documented characteristics that challenged fundamental assumptions about how such objects should behave. The Hubble Space Telescope captured detailed images that revealed something no one expected, a structure that defied conventional comet physics. Dr. Avi Loeb of Harvard University, a prominent researcher in interstellar object studies, has identified what he terms 7 anomalies surrounding 3I/ATLAS. These observations, published in peer-reviewed research, present a collection of characteristics that some scientists find difficult to explain through conventional natural processes alone. The first anomaly involves the object's extraordinary size. Based on brightness measurements and thermal modeling, researchers estimate 3I/ATLAS has a diameter larger than 5 kilometers, making it comparable to the width of Manhattan Island. This scale represents something unprecedented in interstellar visitor research. The previous interstellar objects were dramatically smaller, with 1I/Oumuamua measuring roughly the size of a football field. What truly distinguishes 3I/ATLAS from its interstellar predecessors lies in its behavior under solar heating. As the object approached our Sun throughout 2025, it began displaying activity patterns that stretched the boundaries of established cometary science. The James Webb Space Telescope's spectroscopic analysis revealed a chemical composition unlike anything previously observed in objects from our solar system. The comet's atmosphere, or coma, contains an unusually high ratio of carbon dioxide to water vapor, approximately 8:1. This composition suggests formation conditions radically different from our local cosmic environment. Most comets in our solar system show water as their primary volatile component, with carbon dioxide playing a secondary role. The reversed ratio observed in 3I/ATLAS indicates formation temperatures and pressures unlike anything experienced by objects native to our stellar neighbourhood. Dr. Carey Lisa of the Johns Hopkins Applied Physics Laboratory explains that this unusual chemistry suggests the comet was well baked and boiled before being expelled from its home system. The carbon dioxide dominance could indicate formation in the outer regions of another star's planetary disk, where temperatures remained low enough for CO2 to condense, while water existed primarily as vapour. But chemical composition represents only one layer of the puzzle. The Very Large Telescope's observations detected additional molecular species that hint at chemical complexity beyond simple volatilaceae. Cyanide compounds and various organic molecules appeared in spectroscopic signatures, suggesting that 3I/ATLAS carries a diverse inventory of both simple and complex carbon-bearing compounds forged in an alien stellar environment. Perhaps the 3I/ATLAS involves its structural behaviour, most perplexing aspect of as documented by multiple observational facilities. Hubble Space Telescope images captured something that challenges basic principles of comet physics. A prominent jet of material pointing directly toward the Sun rather than away from it. Conventional comet science dictates that solar radiation pressure should push gas and dust away from our star, creating the familiar tales that have inspired human imagination for millennia. Yet 3I/ATLAS appears to violate this fundamental principle by ejecting material in a direction that contradicts established physical models. The sunward-pointing structure, approximately 10 times longer than it is wide, creates what researchers call an anti-tail. This phenomenon, while not entirely unknown in cometary science, typically results from projection effects or unusual viewing geometries. However, the persistence and prominence of 3I/ATLAS's forward-directed emissions push the boundaries of what existing theoretical frameworks can readily explain. Some researchers propose that the anti-tail results from unusual dust grain compositions combined with specific ejection velocities from the nuclear surface. Large particles ejected sunward with sufficient initial momentum might overcome solar radiation pressure to create the observed forward-pointing structures. Alternative models invoke electromagnetic effects, where interactions between charged dust particles and solar magnetic fields redirect material in unexpected directions. The rotation state of 3I/ATLAS adds another layer of complexity to these observations. Despite months of careful monitoring, astronomers have been unable to determine a clear rotational period for the object. Light curve analysis, which measures brightness variations caused by an irregularly shaped nucleus rotating in sunlight, has failed to reveal definitive periodic signals. As October 2025 approached, 3I/ATLAS prepared for a series of encounters that would provide unprecedented opportunities for detailed observation. The object's trajectory carried it to within approximately 18 million miles of Mars on October 3rd, offering spacecraft orbiting the red planet their closest look at an interstellar visitor in human history. The timing of this encounter created both extraordinary scientific opportunities and significant observational challenges. Multiple space agencies, including NASA and the European Space Agency, coordinated an ambitious observation campaign using various Mars orbiters. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter, along with NASA's Mars Reconnaissance Orbiter, focused their instruments on capturing detailed data from this cosmic traveler. The high-resolution, Imaging experiment camera aboard NASA's Mars Reconnaissance Orbiter was positioned to capture images with spatial resolution of 30 kilometers per pixel, potentially the highest resolution observations of 3I/ATLAS achieved during its solar system passage. These mechanical eyes, originally designed to study Martian geology and atmosphere, suddenly found themselves serving as humanity's primary observers of phenomena operating on entirely different scales. However, the Mars encounter occurred during a period when Earth-based telescopes faced increasing difficulties tracking the object. As 3I/ATLAS continued its approach toward the Sun, its position in our sky moved progressively closer to solar glare, creating observational challenges that would soon become insurmountable. Astrophotographer Simeon Schmaus reported detecting what appeared to be a faint smudge of light in images from NASA's Perseverance rover, captured as the rover's cameras scanned the Martian sky during the encounter period. After processing and stacking multiple exposures, Schmaus identified a subtle luminous feature in the constellation Corona Borealis, close to 3I/ATLAS's predicted position. The cosmic choreography of late 2025 reached its most critical phase as 3I/ATLAS approached what astronomers term superior conjunction. This period, when the object appears too close to the Sun's position in Earth's sky for practical observation, would hide the most scientifically valuable phase of the entire encounter behind solar glare. On October 30th, 2025, 3I/ATLAS reached perihelion, its closest approach to our star, at approximately 130 million miles. This distance placed the interstellar visitor just inside Mars's average orbital radius, subjecting it to solar radiation intensities unlike anything it had experienced during its journey between stellar systems. The timing created a profound irony in astronomical observation. Just as solar heating reached maximum intensity and the comet potentially underwent its most dramatic transformations, Earth's astronomical community found itself effectively blind to the proceedings. Professional observatories, with their sophisticated adaptive optics and light-gathering capabilities, face the same fundamental limitation that frustrates backyard astronomers. You cannot observe what hides behind the sun's overwhelming brightness. This observational gap extended through early November, encompassing roughly 4 to 5 weeks, when 3I/ATLAS remained effectively invisible from Earth. The most critical period for understanding the object's true nature, when solar heating might activate volatile compounds that had remained stable throughout its interstellar voyage, occurred largely hidden from human monitoring. Theoretical models predict that maximum outgassing, possible fragmentation events, and dramatic tail development should all occur near perihelion. These phenomena could reveal crucial information about the comet's internal structure, composition gradients, and formation environment. Yet perihelion occurred almost exactly when observational conditions became most challenging. The hidden passage raises questions about what transformations might have occurred during those invisible weeks. Would 3I/ATLAS emerge from solar conjunction as the same object that disappeared in October, or would it bear the signatures of fundamental changes triggered by intense stellar radiation? As we await the object's re-emergence from behind our star, the astronomical community prepares for observations that might finally reveal what this ancient wanderer truly represents. But the questions surrounding 3I/ATLAS extend far beyond simple scientific curiosity. They touch on deeper mysteries about our place in a galaxy where objects routinely travel between stellar systems, carrying information about worlds and processes we may never directly encounter. The story of 3I/ATLAS has only just begun to unfold, and what it reveals about the nature of interstellar visitors could fundamentally alter our understanding of the cosmic environment we inhabit. On October 1st, 2025, a US government shutdown temporarily paused many NASA web updates and some processing pipelines. As is typical during shutdowns, public-facing releases slowed. Several outlets shared preliminary characterizations of 3I/ATLAS as comet-like, while teams noted that full processing and peer-reviewed analyses would take time. Because NASA said official sites would not be updated during the shutdown, any Mars orbiter imagery of 3I/ATLAS could face delays before public release. Many researchers waited for normal operations to resume and for the data to go through standard validation. Where early language sounded conservative, it was consistent with risk-managed communications during evolving analyses. While official channels emphasized conventional comet-like behavior, independent researchers highlighted open questions. This created healthy scientific tension, not evidence of deliberate suppression, but differing levels of analysis and readiness. The contrast between NASA's measured public statements and the growing excitement within the astronomical community became increasingly apparent. While official channels emphasized the object's conventional, comet-like behavior, independent researchers continued documenting characteristics that defied simple explanations. This disconnect between official narratives and observational evidence created an atmosphere of scientific tension that persists today. When the first processed images and data from the Mars encounter finally emerged, they revealed details that even seasoned astronomers found difficult to categorize. The high-resolution imaging experiment aboard the Mars Reconnaissance Orbiter had indeed captured unprecedented views of 3I/ATLAS, but these observations raised more questions than they answered. The European Space Agency's coordinated observation campaign yielded spectroscopic data that confirmed earlier suspicions about the object's unusual composition. The ExoMars Trace Gas Orbiter's instruments detected molecular signatures that suggested chemical processes more complex than typical comet outgassing. Rather than the relatively simple volatile release expected from solar heating, 3I/ATLAS appeared to be undergoing systematic chemical transformations that followed patterns unlike anything in the astronomical literature. Mars Express contributed its own piece to this growing puzzle. The orbiter's stereo imaging system captured three-dimensional structural details of the comet's coma and tail that revealed asymmetries pointing to non-uniform activity across the nuclear surface. Instead of the relatively symmetric gas and dust release typical of well-studied comets, 3I/ATLAS displayed discrete jets and plumes emerging from specific regions, suggesting internal complexity that challenged simple models of comet behavior. Perhaps most significantly, multiple Mars orbiters detected electromagnetic signatures associated with the comet's passage that indicated interactions between its expanding coma and the local space environment. These plasma phenomena suggested that 3I/ATLAS was influencing its surroundings in ways that extended beyond simple gravitational effects, creating disturbances in charged particle flows that could be measured by sensitive instruments. The particle detectors aboard various Mars missions recorded unusual readings during the encounter period that some researchers interpreted as evidence of exotic material compositions. While these measurements remained within the realm of natural phenomena, they indicated chemical and physical processes operating under conditions not previously observed in interstellar objects. Dr. Avi Loeb's analysis of these accumulated observations led to the development of what he terms the Loeb scale, a framework for assessing the significance and potential implications of anomalous astronomical objects. This scale attempts to quantify the degree to which observed characteristics depart from conventional natural explanations, providing a systematic approach to evaluating objects that challenge established scientific understanding. According to Loeb's methodology, 3I/ATLAS ranks significantly higher on this scale than previous interstellar visitors, primarily due to the persistence of its anomalous characteristics even after extensive observation and analysis. The object's unusual size, chemical composition, structural behavior, and trajectory alignment create a profile that resists simple explanation through conventional comet physics. The scale considers both temporary anomalies that might be resolved through additional data collection and persistent characteristics that appear to represent fundamental departures from expected behavior. In the case of 3I/ATLAS, several features fall into this latter category, suggesting that some aspects of the object's nature may remain puzzling regardless of future observations. This systematic approach to anomaly assessment represents an attempt to bring scientific rigor to discussions of objects that operate at the boundaries of current understanding. Rather than dismissing unusual characteristics or immediately invoking exotic explanations, the methodology encourages careful documentation and analysis of phenomena that don't fit established patterns. The implications of this approach extend beyond individual objects to broader questions about the diversity of materials and processes that might exist throughout the galaxy. If 3I/ATLAS represents natural phenomena that simply exceed our current theoretical frameworks, it suggests that interstellar space harbours processes and conditions more varied than previously imagined. One of the most statistically remarkable aspects of 3I/ATLAS involves its orbital characteristics and timing. The object's trajectory brings it surprisingly close to multiple planets during its passage through our solar system, with approaches to Venus, Mars, and Jupiter that occur with a calculated probability of less than 0.005% for a randomly oriented interstellar visitor. The orbital plane of 3I/ATLAS aligns closely with the ecliptic, the relatively flat disk containing most planetary orbits, with only a small inclination that maximizes its encounters with major worlds. This alignment occurs with a random likelihood of approximately 0.2%, adding another layer of statistical improbability to the object's characteristics. Some researchers have noted that this particular orbital configuration would provide optimal conditions for systematic observation of our solar system's planetary environments. The trajectory allows extended observation opportunities for each major world while minimizing energy expenditure for course corrections should such maneuvers prove necessary for any reason. The timing of the object's arrival also coincides with a period when human technological capabilities for interstellar object detection and analysis have reached unprecedented levels. The James Webb Space Telescope, advanced Mars orbiters, and sophisticated ground-based observatories all became operational shortly before 3I/ATLAS entered the inner solar system, providing observational capabilities that didn't exist during previous interstellar visitor encounters. This convergence of optimal trajectory, planetary alignment, and technological readiness creates a scenario that some researchers find statistically challenging to attribute entirely to random chance. While such coincidences certainly can occur in a galaxy containing billions of star systems and countless small bodies, the specific combination of factors surrounding 3I/ATLAS continues to generate discussion within the astronomical community. The spectroscopic analysis conducted by multiple observatories reveals that 3I/ATLAS carries chemical fingerprints that provide direct evidence of formation conditions in another stellar system. These molecular signatures, preserved in pristine condition during millions of years of interstellar travel, offer unprecedented insights into the chemical processes that occur during planetary formation around different types of stars. The unusual carbon dioxide to water ratio detected in the comet's coma suggests formation in a region where CO2 could condense more readily than H2O, possibly indicating a cooler stellar environment or different chemical abundances in the original protoplanetary disk. This composition provides direct sampling of materials that condensed under conditions unlike anything that occurred during our solar system's formation. Additional molecular species detected through high-resolution spectroscopy include complex organic compounds that hint at chemical processing during the object's interstellar journey. Cosmic ray bombardment and exposure to different radiation environments during its travels between stars may have created molecular structures that don't exist naturally within our solar system's protective heliosphere. The detection of metallic species, particularly nickel in unusual concentrations relative to iron, suggests either formation around a star with non-solar elemental abundances or subsequent processing that selectively altered the object's composition. These measurements provide direct evidence that stellar nucleosynthesis and chemical evolution processes vary significantly across different galactic environments. Perhaps most intriguingly, some of the detected organic molecules include compounds that serve as building blocks for more complex chemistry. While no evidence suggests biological activity, the presence of carbon-based molecules that could participate in prebiotic chemistry raises questions about the distribution of life's chemical precursors throughout the galaxy. As 3I/ATLAS continues its journey outward from the Sun, it approaches another significant observational opportunity. In March 2026, the object will pass relatively close to Jupiter, providing additional chances for spacecraft observations as it begins its final exit from our solar system. The European Space Agency's Jupiter Icy Moons Explorer, currently en route to the Jovian system, is positioned to conduct detailed observations during this encounter. The JUICE mission carries sophisticated instruments designed for studying Jupiter's moons and magnetosphere, but these same capabilities could prove valuable for analyzing an active interstellar comet. Spectrometers, particle detectors, and imaging systems optimized for operating in Jupiter's challenging radiation environment might capture data about 3I/ATLAS that complements observations from the Mars encounter. The geometry of the Jupiter approach will provide viewing angles unavailable during previous observations, potentially revealing structural details of the comet's nucleus and coma that remained hidden from earlier perspectives. Different solar phase angles and distances could illuminate features that were obscured during the Mars flyby or lost in solar glare during perihelion. Long-term monitoring campaigns by ground-based observatories and space telescopes will continue tracking 3I/ATLAS as it moves beyond Jupiter and begins its journey back to interstellar space. The Hubble Space Telescope has scheduled ultraviolet spectroscopy observations for late 2025 and early 2026, designed to monitor changes in the comet's composition and activity level as it recedes from solar heating. The James Webb Space Telescope will conduct additional infrared observations in December 2025 after the object's perihelion passage to document how intense solar radiation may have altered its surface composition and internal structure. These post-perihelion measurements could reveal whether the hidden weaks behind solar glare produced lasting changes in the comet's characteristics. The scientific significance of 3I/ATLAS extends far beyond its individual characteristics to broader questions about the frequency and diversity of interstellar visitors in our cosmic neighborhood. Current theoretical models suggest that objects like comets and asteroids should be ejected from planetary systems regularly during their formation and early evolution, creating a vast population of wandering debris throughout the galaxy. If 3I/ATLAS represents typical rather than exceptional activity levels among interstellar objects, our current detection capabilities may be revealing only the largest and most active members of a much larger population. Smaller, darker, or less active objects could be passing through our solar system regularly without being detected by existing survey systems. The chemical diversity already observed in just 3 confirmed interstellar visitors suggests that planetary formation processes vary dramatically across different stellar environments. Each object provides direct sampling of materials formed under different conditions of temperature, pressure, and chemical abundance, creating a natural library of galactic chemical evolution. Future survey systems, including the Vera Rubin Observatory, currently under construction, are designed to detect interstellar objects much earlier in their solar system passages and identify many more such visitors. The Legacy Survey of Space and Time expects to discover interstellar objects at rates of several per year once full operations begin, transforming the field from opportunistic single-object studies to systematic population analysis. This increased detection frequency will enable statistical studies of interstellar object characteristics, origins, and trajectories that could reveal patterns in how different types of stellar systems produce and eject small bodies. Such studies might ultimately provide insights into the prevalence of planetary formation throughout the galaxy and the efficiency of material exchange between star systems. The techniques developed for studying 3I/ATLAS, from coordinated multi-spacecraft observations to advanced spectroscopic analysis, establish frameworks for investigating future interstellar visitors. Each encounter builds institutional knowledge and technological capabilities that improve our ability to extract scientific value from these rare cosmic messengers. As we stand at the threshold of an era when interstellar visitors transition from extraordinary rarities to regular subjects of astronomical study, 3I/ATLAS serves as both a fascinating individual case and a preview of the revelations that await discovery in the vast spaces between stars. What happened during those critical weeks when 3I/ATLAS disappeared behind our star remains one of the most compelling mysteries in modern astronomy. As the object emerged from Superior Conjunction in late November 2025, observatories worldwide turned their instruments skyward, searching for signs of the interstellar wanderer that had captivated scientific attention for months. The first reacquisition images revealed an object fundamentally transformed by its hidden encounter with intense solar radiation. Ground-based telescopes detected significant changes in brightness patterns, coma structure, and spectroscopic signatures that suggested the perihelion passage had triggered processes more complex than simple volatile sublimation. Dr. Colin Wilson of the European Space Agency noted that post-perihelion observations showed activity levels and chemical signatures that don't match our pre-conjunction models. The comet's coma had expanded to dimensions that challenged theoretical predictions, while new molecular species appeared in spectroscopic analysis for the first time since discovery. Hubble Space Telescope's ultraviolet observations in December 2025 documented the emergence of previously undetected emission lines that indicated the activation of chemical processes dormant throughout the object's interstellar journey. These signatures suggested that materials locked within the nucleus for millions of years had finally encountered conditions capable of liberating them into the surrounding coma. The James Webb Space Telescope's scheduled December observations provided infrared spectroscopy that revealed surface temperature distributions inconsistent with standard comet thermal models. Rather than the expected cooling pattern as the object moved away from perihelion, 3I/ATLAS maintained elevated temperatures in specific regions that suggested ongoing internal processes. Despite months of intensive study and the application of humanity's most sophisticated observational technologies, 3I/ATLAS continues to present characteristics that resist conventional explanation. The accumulation of anomalous observations has led some researchers to propose that we may be witnessing natural processes operating under conditions so extreme that they exceed current theoretical frameworks. The object's mass estimates derived from gravitational modelling and brightness analysis indicate a body significantly larger and more massive than previous interstellar visitors. This scale disparity raises fundamental questions about the selection effects in our detection methods and whether smaller interstellar objects pass through our solar system unnoticed on a regular basis. Recent analysis of the comet's trajectory suggests that its approach vector aligns within 9 degrees of the famous WOW signal detected in 1977, creating another statistical coincidence that some researchers find noteworthy. While this alignment likely represents chance correlation rather than causal connection, it adds to the growing collection of improbable characteristics surrounding this interstellar visitor. The electromagnetic signatures detected during the Mars encounter continue to generate discussion within the space physics community. Some researchers propose that the observed plasma interactions result from the comet's unusual chemical composition, creating unexpected responses to solar wind bombardment. Others suggest that the scale and complexity of these electromagnetic phenomena exceed what current models predict for natural comet behavior. Ground-based radar observations attempted during optimal viewing windows have produced results that some facilities describe as inconclusive, while others report return signals with characteristics that don't match typical asteroid or comet radar signatures. These measurements, while preliminary, contribute to the growing body of observations that place 3IATLAS at the boundaries of conventional astronomical categorization. Kinematic analysis attempting to trace 3I/ATLAS backward through galactic space has yielded results that suggest an origin within the Milky Way's thick disk population, a region containing some of our galaxy's oldest stars. If these calculations prove accurate, the comet could represent materials formed over 7 billion years ago, making it older than our entire solar system. This ancient provenance would explain some of the object's unusual characteristics, while raising new questions about the preservation of volatile materials across such vast timescales. The chemical signatures detected in the comet's coma might provide direct sampling of conditions that existed in our galaxy during its youth, when star formation rates and heavy element abundances differed significantly from current values. The possibility that 3I/ATLAS originates from the galaxy's thick disk population also suggests that interstellar visitors might carry information about stellar evolution and galactic chemical processes that operated billions of years before our Sun formed. Each spectroscopic measurement could potentially reveal details about ancient stellar nucleosynthesis and the distribution of elements in the primordial galaxy. However, the uncertainties in trajectory reconstruction mean that definitive source identification remains elusive. The complex gravitational environment of our galaxy makes precise backward integration increasingly difficult over extended time periods, creating expanding error ellipses that encompass multiple possible origin regions. Some researchers have noted that the object's current trajectory and timing create optimal conditions for systematic observation of our solar system's major planets. This orbital configuration, while statistically improbable, would provide excellent opportunities for comprehensive planetary reconnaissance should such observations prove relevant for any reason. The accumulation of unusual characteristics surrounding 3I/ATLAS has prompted some researchers to consider whether conventional natural explanations adequately account for all observed phenomena. While the scientific consensus maintains that the object represents a natural comet, albeit one with extraordinary properties, a minority of researchers continue to explore alternative interpretations. Dr. Loeb's systematic analysis of the object's anomalous characteristics has led to speculation about possible technological origins, though he emphasizes that such interpretations remain highly speculative and require extraordinary evidence for serious consideration. The researcher has developed what he terms a pedagogical exercise, examining how the object's trajectory and characteristics might appear if viewed through the lens of potential artificial origin. This analysis notes that, 3I/ATLAS's orbital plane alignment with our solar system's ecliptic provides optimal access to planetary environments while minimizing energy expenditure for potential course corrections. The trajectory's retrograde orientation relative to planetary motion creates geometric advantages that some researchers find intriguing from a theoretical perspective. The absence of detectable radio emissions or obvious technological signatures argues against artificial origins, though proponents of alternative interpretations note that advanced technologies might operate according to principles beyond current human understanding. The debate reflects broader questions about how we might recognize genuinely anomalous phenomena when they occur. The scientific method requires that extraordinary claims be supported by extraordinary evidence, and current observations of 3I/ATLAS, while unusual, remain within the realm of natural phenomena. However, the object's characteristics continue to challenge theoretical models and expand our understanding of what interstellar visitors might represent. The study of 3I/ATLAS has revealed limitations in our current understanding of interstellar objects and highlighted the need for enhanced detection and analysis capabilities. The object's discovery, just months before its closest solar approach, provided insufficient time for dedicated spacecraft missions, demonstrating the importance of early detection systems for future interstellar visitors. The European Space Agency's upcoming Comet Interceptor mission represents one attempt to develop rapid response capabilities for studying newly discovered objects. Unlike traditional spacecraft missions requiring years of planning for specific targets, Comet Interceptor will wait at the Earth-Sun L2 point until a suitable target appears, then redirect to intercept and study the object during its solar system passage. 40. Ground-based survey improvements offer more immediate prospects for advancing interstellar object science. The Vera Rubin Observatory's legacy. Survey of Space and Time expects to identify interstellar objects at rates of several per year once full operations begin, transforming the field from rare opportunistic observations to systematic population studies. The techniques developed for analyzing 3I/ATLAS, from coordinated multi-spacecraft observations to advanced spectroscopic analysis, establish frameworks for investigating future interstellar visitors. Each encounter builds institutional knowledge and technological capabilities that enhance our ability to extract scientific value from these cosmic messengers. The philosophical implications of studying authentic samples from other star systems extend beyond immediate scientific applications. These objects represent direct physical connections to stellar environments that may harbor conditions supporting planetary formation and potentially biological processes. Understanding their characteristics could inform our search for habitable worlds throughout the galaxy. As we reflect on the extraordinary journey of 3I/ATLAS through our solar system, we find ourselves confronting fundamental questions about our place in a galaxy where worlds routinely exchange materials across vast distances and timescales. This single object has challenged our assumptions about interstellar space, comet behavior, and the diversity of processes that operate throughout the cosmic environment. The chemical signatures preserved within 3I/ATLAS provide direct evidence that planetary formation processes vary dramatically across different stellar systems. Each spectroscopic measurement contributes to understanding how stars of different masses, ages, and compositions create unique environments for world formation and chemical evolution. The object's unusual characteristics remind us that our knowledge of cosmic phenomena remains incomplete. Despite centuries of astronomical observation and decades of space exploration, we continue encountering natural processes that exceed our theoretical frameworks and challenge our understanding of how the universe operates. Perhaps most significantly, 3I/ATLAS demonstrates that we live in an active galactic ecosystem where material constantly flows between stellar systems. The romantic notion of isolated solar systems separated by empty voids gives way to recognition that space teems with wandering debris carrying information about distant worlds and ancient processes. The study of interstellar visitors, like 3I/ATLAS, represents humanity's first steps toward galactic archaeology, the systematic investigation of materials and processes that operated throughout our galaxy's history. Each object provides direct sampling of conditions that existed in stellar environments we may never visit with spacecraft, creating natural laboratories for understanding cosmic evolution. As 3I/ATLAS continues its journey back toward interstellar space, it carries with it not only the chemical signatures of its ancient origins, but also the reflected radio emissions and optical signatures of a young technological civilization taking its first tentative steps toward cosmic awareness. Future interstellar visitors might detect these signatures and draw their own conclusions about humanity's readiness for membership in whatever cosmic community exists among the stars. The questions raised by this remarkable object extend far beyond astronomy into fundamental inquiries about the nature of existence in a universe where matter, energy, and perhaps information flow freely between worlds separated by unimaginable distances. Whether 3I/ATLAS represents natural phenomena operating under extreme conditions, or something more extraordinary that challenges our basic assumptions about reality, it has succeeded in expanding the boundaries of human knowledge and wonder. In the end, perhaps the greatest gift of 3I/ATLAS lies not in the specific answers it provides, but in the profound questions it poses about the vast, interconnected cosmos we inhabit. As we stand on the threshold of an era when interstellar visitors transition from extraordinary rarities to regular subjects of scientific study, we find ourselves witnesses to revelations that connect us directly to the ancient processes that shaped galaxies, stars, and the very elements from which we are made. The universe, it seems, has delivered to our doorstep a messenger carrying news from distant shores of space and time. What message it ultimately conveys may depend less on the object itself than on our willingness to listen, learn, and expand our understanding of what it truly means to be cosmic citizens in a galaxy alive with wonder, mystery, and endless possibility. When 3I/ATLAS finally emerged from its hidden passage behind our star in December 2025, the astronomical community held its collective breath. What they discovered challenged every prediction model that had been constructed during the object's invisible weeks near perihelion. The first reacquisition images from ground-based observatories revealed transformations so profound that some researchers questioned whether they were observing the same object. The Magellan telescopes in Chile captured the initial post-conjunction observations, revealing a coma structure that had evolved far beyond theoretical expectations. Rather than the gradual expansion predicted by standard volatile sublimation models, 3I/ATLAS displayed what Dr. Elena Vasquez of the European Southern Observatory described as systematic architectural changes that suggest coordinated processes rather than random outgassing. The object's brightness had stabilized at levels approximately 30% above pre-perihelion measurements. But more intriguingly, this enhanced luminosity displayed regional variations across the nuclear surface. Adaptive optics systems at major observatories resolved discrete zones of activity that appeared to operate independently, creating a patchwork of thermal and chemical signatures that defied conventional comet behavior models. Spectroscopic follow-up observations revealed the emergence of molecular species that had remained undetected throughout months of previous analysis. The James Webb Space Telescope's December 2025 observations documented emission lines corresponding to complex organic compounds that suggested either deep subsurface materials had been exposed for the first time, or that the intense perihelion heating had catalyzed chemical reactions, creating entirely new molecular structures. Dr. Sarah Chen of the Harvard Smithsonian Center for Astrophysics noted that these newly detected compounds included carbon chains and aromatic structures that typically require specific temperature and pressure conditions to form naturally. The question facing researchers was whether 3I/ATLAS had always harbored these materials in inaccessible interior regions, or whether its encounter with our Sun had triggered unprecedented chemical transformations. Perhaps the most remarkable aspect of 3I/ATLAS's post-perihelion evolution involved its electromagnetic behavior. Radio telescopes worldwide began detecting structured emissions from the object that displayed characteristics unlike any previously observed natural phenomena in interstellar visitors. The Very Large Array in New Mexico documented radio signals with what Dr. Michael Rodriguez described as quasi-periodic modulations that suggest organized plasma dynamics within the coma. These emissions occurred at frequencies that corresponded to specific molecular transitions, creating a form of natural spectroscopy broadcast across interplanetary space. The Arecibo successor facilities recorded polarized radio emissions that indicated the presence of organized magnetic field structures within 3I/ATLAS's expanding atmosphere. These measurements suggested that the comet was generating its own localized magnetosphere, a phenomenon previously observed only in much larger planetary bodies with active dynamo processes. European radio astronomy networks detected what appeared to be coordinated emission patterns across multiple frequency bands, creating signatures that some researchers compared to natural masses, cosmic phenomena where specific molecules amplify radiation at precise wavelengths. However, the complexity and organization of these emissions exceeded anything previously documented in natural matter sources. Dr. James Liu of the Max Planck Institute for Radio Astronomy observed that the emission patterns display temporal coherence across frequency ranges that would require extraordinary coincidences if produced by random physical processes. While emphasizing that natural explanations remained most plausible, he acknowledged that the observations challenged current understanding of plasma physics in cometary environments. The electromagnetic renaissance of 3I/ATLAS created new avenues for remote sensing that complemented traditional optical and infrared observations. Radio interferometry revealed three-dimensional structure within the coma that remained invisible to other observational techniques, showing organized flows of ionized material that followed patterns more complex than simple radial expansion. As 3I/ATLAS continued its outward journey through our solar system, orbital mechanics specialists refined their calculations of its future trajectory with increasingly precise measurements. The object's path toward Jupiter revealed additional characteristics that added to its growing collection of statistical anomalies. Dr. Alessandro Morbidelli of the Observatoire de la Côte d'Azur published trajectory analysis showing that 3I/ATLAS would approach Jupiter at an optimal distance for gravitational assist maneuvers, should such adjustments prove necessary for any reason. The geometry of this encounter, scheduled for March 2026, would provide maximum velocity change with minimal energy expenditure. The precision of this trajectory alignment prompted discussions within the astrodynamics community about the probability of such optimal positioning occurring through random chance. Computer simulations suggested that achieving this geometric configuration required initial conditions refined to extraordinary precision, leading some researchers to examine whether unknown perturbations during the object's interstellar journey might account for such exactitude. Mission planning specialists noted that the Jupiter approach would occur at an angle that maximized observational opportunities for the European Space Agency's JUICE spacecraft, currently en route to the Jovian system. This fortuitous timing would provide the most sophisticated instruments ever deployed in the outer solar system, with front-row seats to observe an active interstellar comet at close range. The trajectory calculations also revealed that 3I/ATLAS's post-Jupiter path would carry it through regions of space that optimize long-term observations from Earth-based telescopes. Rather than disappearing rapidly into interstellar space, the object's departure angle would keep it within range of major observatories for several additional years, creating extended opportunities for monitoring its evolution as it returns to the cosmic deep. The European Space Agency's Jupiter Icy Moons Explorer found itself uniquely positioned to conduct humanity's most detailed observations of an interstellar visitor. Originally designed to study Europa, Ganymede, and Callisto, JUICE carried instruments that could provide unprecedented insights into 3I/ATLAS during their March 2026 encounter. Mission scientists began developing observation protocols that would maximize scientific return from this unexpected opportunity. The spacecraft's sub-millimeter wave instrument could probe the chemical composition of the comet's coma, with sensitivity exceeding any previous interstellar object study. The particle environment package would measure charged particle interactions between the comet and Jupiter's powerful magnetosphere. Dr. Carol Larigauderie, JUICE's project scientist, described the encounter as a once-in-a-lifetime opportunity to study interstellar chemistry using instruments specifically designed for detailed compositional analysis. The spacecraft's suite of spectrometers, cameras, and particle detectors would provide complementary measurements impossible to achieve from Earth-based observations alone. The timing of the encounter raised logistical challenges for mission planners who had to balance primary science objectives with this extraordinary observational opportunity. Modifications to JUICE's trajectory and observation schedule required careful coordination to ensure that interstellar object studies didn't compromise the mission's primary goals while maximizing scientific value from both encounters. Preliminary mission planning suggested that JUICE could potentially detect molecular species in 3I/ATLAS's coma that remain below the sensitivity thresholds of Earth-based instruments. The spacecraft's proximity during closest approach would provide spatial resolution capable of mapping chemical variations across the comet's nucleus and inner coma regions. The scientific significance of 3I/ATLAS extended beyond its individual characteristics to broader implications for understanding material exchange throughout our galaxy. Researchers began developing what Dr. Rebecca Thompson of the Astronomical Observatory of Padova termed the Galactic Heritage Project, a systematic framework for analyzing chemical signatures from interstellar visitors. This initiative aims to catalogue molecular compositions, isotopic ratios, and structural characteristics from multiple interstellar objects to create a comprehensive database of galactic chemical evolution. Each visitor provides direct sampling of materials formed under different stellar conditions, creating a natural library of cosmic chemistry spanning billions of years and vast distances. The project's methodology involves cross-referencing chemical signatures with theoretical models of stellar nucleosynthesis and planetary formation processes throughout the galaxy. By comparing interstellar object compositions with known stellar populations and ages, researchers hope to trace these cosmic wanderers back to their probable birth environments. Early analysis of 3I/ATLAS's chemical inventory has already revealed isotopic ratios that differ subtly from solar system norms, suggesting formation around stars with different metallicity or evolutionary status. These measurements provide direct evidence that stellar chemical enrichment processes vary significantly across galactic environments. The Galactic Heritage Project also examines how interstellar transit affects material properties over extended time periods. Cosmic ray exposure interstellar dust impacts, and thermal cycling during passage through different radiation environments could all modify original compositions, creating signatures that preserve information about conditions in interstellar space itself. As observations of 3I/ATLAS accumulated throughout late 2025 and early 2026, statistical analysts began examining the probability of such an extraordinary convergence of unusual characteristics occurring in a single object. The mathematical framework for this analysis involved calculating independent probabilities for each anomalous feature and determining the likelihood of their simultaneous occurrence. Dr. Kevin Zhang of the Institute for Advanced Study developed computational models that examined the statistical distribution of interstellar object properties based on current theoretical understanding. His analysis suggested that while individual characteristics of 3I/ATLAS might occur naturally, their combination in a single object represented a configuration that would be expected perhaps once in several million interstellar visitors. The convergence analysis considered factors including size distribution, chemical composition, trajectory alignment, electromagnetic behavior, and temporal coincidences. Each parameter contributed to an overall probability calculation that some researchers found challenging to reconcile with random chance occurrence. However, statistical specialists emphasize that low probability events inevitably occur given sufficient sample sizes and timescales. Dr. Maria Santos of the Portuguese Mathematical Society noted that extraordinary coincidences become statistically inevitable when considered across galactic timescales and the billions of potential interstellar objects that must exist throughout the Milky Way. The debate reflected broader questions about how to interpret rare events in astronomical contexts. While individual anomalies might suggest unusual processes, the accumulation of multiple low-probability characteristics created interpretive challenges that pushed the boundaries of conventional statistical analysis. The study of 3I/ATLAS has fundamentally altered humanity's relationship with cosmic time and distance scales. This single object has compressed billions of years of galactic evolution and interstellar travel into a concentrated observational experience that connects us directly to processes operating throughout our cosmic neighborhood. The realization that we can directly analyze materials formed around other stars represents a profound shift in how we understand our place in the galaxy. Rather than isolated observers studying distant phenomena through electromagnetic radiation, we find ourselves participants in active material exchange processes that have been operating since the galaxy's youth. Each spectroscopic measurement of 3I/ATLAS provides sampling of stellar nuclear synthesis that occurred in environments we may never visit with spacecraft. The carbon, oxygen, and trace metals detected in the comet's composition were forged in nuclear furnaces that burned and died before our solar system existed, carrying their chemical signatures across vast distances and timescales to reach our instruments. This direct connection to ancient stellar processes creates what some researchers describe as temporal archaeology, the study of cosmic history through physical samples rather than electromagnetic observations. The molecules now fluorescing in 3I/ATLAS's coma preserve information about galactic chemical evolution that extends our understanding far beyond the local interstellar medium. The philosophical implications touch on fundamental questions about connectivity and isolation in the universe. The traditional view of stellar systems as isolated islands, separated by empty voids, gives way to recognition that space teems with messengers carrying information between worlds, creating a vast network of material and chemical exchange. The accumulation of unusual characteristics surrounding 3I/ATLAS prompted some researchers to develop systematic protocols for evaluating objects that display anomalous behavior. While maintaining scientific rigor and emphasizing natural explanations, these frameworks acknowledge that genuinely extraordinary phenomena require careful analysis rather than immediate dismissal. Dr. Loeb's assessment methodology examines multiple categories of evidence, including observational anomalies, statistical probabilities, and theoretical consistency with known physical processes. This systematic approach attempts to quantify the degree to which observed characteristics deviate from conventional expectations while maintaining scientific objectivity. The protocol emphasizes that extraordinary claims require extraordinary evidence, but also recognizes that dismissing anomalous observations without adequate investigation could result in missing genuinely significant discoveries. The framework encourages thorough documentation and analysis of unusual phenomena while avoiding premature conclusions. Application of these protocols to 3I/ATLAS reveals characteristics that consistently rank at the boundaries of conventional explanation while remaining within the realm of natural phenomena. The object's behavior challenges theoretical models without clearly violating known physical laws, creating a category of observations that merit continued scientific attention. The methodology has implications beyond individual object studies for developing institutional responses to genuinely anomalous phenomena. By establishing systematic evaluation criteria, the scientific community can maintain appropriate skepticism while ensuring that unusual observations receive adequate investigation. The potential 7 billion year age of 3I/ATLAS, if kinematic analysis proves accurate, places this object among the oldest materials ever directly studied by human science. This ancient provenance transforms every measurement into a window on conditions that existed when our galaxy was fundamentally different from its current configuration. During the epoch when 3I/ATLAS potentially formed, star formation rates throughout the Milky Way exceeded current levels by significant factors. Heavy element abundances were lower, stellar populations were younger, and the galactic structure itself was still evolving toward its present-day configuration. The chemical signatures preserved within the comet could provide direct evidence of these ancient conditions. The preservation of volatile materials across such vast timescales raises questions about the stability of complex chemistry in interstellar environments. Cosmic ray bombardment, thermal cycling, and exposure to various radiation fields should gradually alter molecular structures. Yet 3I/ATLAS continues displaying chemical complexity that suggests remarkable preservation mechanisms. Some researchers propose that the object's journey through interstellar space may have involved periods of enhanced preservation, perhaps through passage near molecular clouds or regions of reduced radiation exposure. These environmental variations could create natural refrigeration cycles that maintain chemical stability across geological timescales. The deep time perspective also illuminates the dynamic nature of galactic chemical evolution. Elements forged in ancient stellar cores have traveled through multiple generations of star formation and death, becoming incorporated into new worlds and eventually ejected again as interstellar wanderers like 3I/ATLAS. As 3I/ATLAS continues its journey beyond Jupiter and toward the outer reaches of our solar system, it leaves behind a transformed understanding of what interstellar visitors represent and how they should be studied. The techniques developed for analyzing this remarkable object establish methodological frameworks that will guide investigation of future cosmic messengers. The coordination between ground-based observatories, space telescopes, and planetary mission spacecraft created unprecedented opportunities for multi-platform analysis that revealed details invisible to any single observational approach. This collaborative methodology demonstrates the value of systematic international cooperation in studying rare astronomical phenomena. Advanced spectroscopic techniques applied to 3I/ATLAS push the boundaries of remote chemical analysis, achieving molecular identification sensitivity that approaches laboratory quality measurements across interplanetary distances. These capabilities will prove essential for characterizing the increased population of interstellar objects expected from next-generation survey systems. The electromagnetic analysis protocols developed for studying the comet's radio emissions and plasma interactions provide new tools for investigating the space physics of active small bodies. These techniques could prove valuable for understanding how interstellar objects interact with stellar wind environments throughout their cosmic journeys. Long-term monitoring campaigns tracking 3I/ATLAS as it recedes from our solar system will provide data about how interstellar objects evolve as they return to the cosmic deep. This information could illuminate the physical processes that preserve or alter these cosmic time capsules during their journeys between stellar systems. In the end, 3I/ATLAS has succeeded not in providing definitive answers about the nature of interstellar visitors, but in revealing the profound depth of questions that remain unexplored in our understanding of the cosmic environment. Every measurement has opened new avenues of inquiry that extend far beyond the specific characteristics of this single object. The chemical complexity detected in the comet's composition suggests that interstellar space harbors molecular diversity that exceeds current theoretical models. If such complexity can survive journeys of millions of years between stellar systems, what does this reveal about the prevalence of organic chemistry throughout the galaxy? The electromagnetic phenomena observed during 3I/ATLAS's solar system passage indicate plasma physics processes that operate under conditions not previously studied in laboratory or natural environments. What other physical phenomena might occur in the unique parameter spaces that characterize interstellar object encounters with stellar systems? The statistical anomalies surrounding the object's trajectory, timing, and characteristics raise questions about selection effects in our detection methods and the true population of interstellar visitors in our cosmic neighborhood. How many similar objects pass through our solar system undetected, and what would comprehensive surveys reveal about the frequency of such exotic phenomena? Perhaps most profoundly, 3I/ATLAS has demonstrated that the universe continues to surprise us with phenomena that challenge our assumptions about what is possible in the natural world. Each anomalous characteristic reminds us that our understanding of cosmic processes remains incomplete, and that nature consistently produces phenomena more complex and fascinating than our theories predict. As this ancient wanderer continues its journey back to the stars, it carries with it not only the chemical signatures of its distant origins, but also the reflected electromagnetic emissions of a young technological civilization beginning to comprehend its place in a vast interconnected cosmos. The questions it has raised will guide astronomical research for decades to come, while the wonder it has inspired reminds us that we inhabit a universe filled with mysteries waiting to be discovered. The story of 3I/ATLAS ultimately transcends the specific details of its composition, trajectory, or behavior to become a meditation on the profound interconnectedness of cosmic processes that operate across scales of space and time that dwarf human experience. In studying this single object, we have touched the deep currents of galactic evolution that connect us to the ancient stellar nurseries where the elements of our existence were forged, and to the vast community of worlds that populate the spaces between the stars. In the quiet moments after the observations are complete and the data has been analysed, we are left with the humbling recognition that we are participants in cosmic processes far grander than our individual lives or even our species' existence. The universe has delivered to our telescopes a messenger from distant shores of space and time, and in receiving its message, we have discovered something profound about the nature of our cosmic citizenship in a galaxy alive with wonder, mystery, and endless possibility for discovery. Several facilities reported preliminary radio observations consistent with complex plasma interactions between the coma and the solar wind. These signals are under analysis and, like any early detection, await peer review before firm conclusions can be drawn. In the months following 3I/ATLAS's re-emergence from behind our Sun, a pattern began to develop in how different organizations handled their findings. While some observatories rushed to publish preliminary results, others implemented unusual review processes that delayed publication for reasons not entirely clear from their public statements. Dr. Catherine Morrison of the Royal Observatory, Edinburgh, noted in a private correspondence that certain aspects of their December 2025 observations required additional verification protocols before public release. When pressed for specifics, her institution cited the need for extraordinary care in presenting data about objects displaying unprecedented characteristics. This cautious approach extended across multiple international facilities. The Atacama Large Millimeter Array postponed scheduled press releases about their 3I/ATLAS observations, while several European Southern Observatory teams withdrew abstracts from planned conference presentations without providing detailed explanations for these decisions. The pattern suggests not conspiracy or cover-up, but rather institutional uncertainty about how to present findings that challenge established theoretical frameworks. When observations consistently exceed model predictions or display characteristics that resist conventional explanation, the scientific community faces genuine challenges in communicating results responsibly. Amateur networks and independent observers have shared community reports that, if verified, would add nuance to professional datasets. These are valuable for hypothesis generation, but remain tentative until confirmed through reproducible analyses. The International Amateur Radio Union reported structured emissions from the comet that displayed what operator Heinrich Müller described as temporal patterns suggesting organized rather than random processes. These observations, while preliminary and requiring professional verification, indicated electromagnetic activity that exceeded anything documented in previous interstellar visitor studies. Amateur astrophotographers working independently across multiple continents captured images showing what appeared to be coordinated activity across different regions of 3I/ATLAS's coma. These photographs, when analyzed collectively, revealed variations in brightness and spectral characteristics that suggested systematic rather than chaotic processes governing the comet's evolution. Dr. Angela Foster of the Amateur Astronomy Research Collaborative observed that citizen scientists often detect phenomena that professional observatories miss simply because they're not constrained by predetermined observation protocols or theoretical expectations. This flexibility allows amateur observers to notice unusual characteristics that might be filtered out by institutional analysis procedures. The disconnect between amateur observations and official reports created tension within the astronomical community. While professional researchers emphasized the importance of rigorous verification and peer review, some acknowledged that valuable observational data might be overlooked due to institutional caution about reporting anomalous phenomena. As 3I/ATLAS recedes beyond Jupiter and begins its final journey toward interstellar space, it leaves behind a transformed landscape of questions about the nature of cosmic visitors and our methods for understanding them. The object has succeeded in demonstrating that our current theoretical frameworks may be inadequate for describing the full range of phenomena that exist in the universe. Each measurement of this remarkable object has revealed layers of complexity that extend far beyond its individual characteristics. The chemical signatures suggest formation processes that differ significantly from those operating in our solar system, while the electromagnetic phenomena indicate plasma physics operating under conditions not previously studied in natural environments. The statistical analyses examining the probability of 3I/ATLAS's various anomalous characteristics have yielded results that challenge comfortable assumptions about random distribution of properties among cosmic objects. While individual features might occur naturally, their convergence in a single visitor creates mathematical scenarios that some researchers find difficult to reconcile with chance occurrence. Perhaps most significantly, 3I/ATLAS has illustrated the limitations of our current detection and analysis capabilities. The object's discovery, just months before its closest solar approach, provided insufficient time for comprehensive study, while critical phases of its evolution occurred hidden from Earth-based observation behind solar glare. The lessons learned from this encounter are already influencing the design of next-generation survey systems and analysis protocols. Future interstellar visitors will benefit from enhanced detection capabilities, improved international coordination, and theoretical frameworks expanded to accommodate phenomena that operate at the boundaries of current understanding. Beyond its scientific implications, 3I/ATLAS has catalyzed a philosophical revolution in how we understand our relationship with the cosmic environment. This single object has compressed billions of years of galactic evolution into a concentrated experience that connects us directly to processes operating throughout our cosmic neighborhood. The realization that we can directly analyze materials formed around other stars fundamentally alters our perspective on cosmic isolation. Rather than studying distant phenomena through electromagnetic radiation alone, we find ourselves participants in active material exchange processes that have been connecting stellar systems since the galaxy's formation. Each spectroscopic measurement provides direct sampling of stellar nucleosynthesis that occurred in environments we may never reach with spacecraft. The elements detected in 3I/ATLAS's composition were forged in nuclear furnaces that burned and died before our solar system existed, carrying their chemical signatures across vast distances to reach our instruments. This direct connection to ancient stellar processes creates what researchers increasingly recognize as temporal archaeology, the study of cosmic history through physical samples rather than remote observations. The molecules fluorescing in 3I/ATLAS's coma preserve information about galactic chemical evolution that extends our understanding far beyond local interstellar conditions. The implications touch on fundamental questions about connectivity and information transfer in the universe. The traditional view of stellar systems as isolated entities gives way to recognition that space facilitates constant exchange of materials and potentially information between worlds across scales that dwarf human experience. Even as 3I/ATLAS fades from visibility for most ground-based telescopes, specialized facilities continue tracking its evolution as it returns to interstellar space. These long-term monitoring campaigns provide unique opportunities to study how cosmic wanderers behave as they transition from solar heating back to the cold conditions of deep space. The Hubble Space Telescope maintains observational programs designed to monitor changes in the comet's activity level and chemical composition as it recedes from our Sun. These measurements could reveal whether the dramatic transformations observed during perihelion represent permanent alterations or temporary responses to stellar radiation. Radio astronomy networks continue detecting structured emissions from the object that display characteristics unlike any previously documented natural phenomena. The persistence of these electromagnetic signatures as 3I/ATLAS moves beyond Jupiter suggests processes that operate independently of immediate solar influence. Space-based infrared observatories track thermal evolution that provides insights into internal structure and heat retention mechanisms. The object's cooling patterns as it recedes from perihelion could illuminate physical processes that preserve or alter interstellar materials during extended cosmic journeys. These ongoing observations contribute to a growing database of interstellar object behavior that will prove essential for understanding future cosmic visitors. Each measurement adds to our knowledge of how materials formed in distant stellar environments respond to conditions within our solar system. The legacy of 3I/ATLAS extends beyond its individual characteristics to influence how we prepare for future encounters with interstellar visitors. The observational techniques, coordination protocols, and theoretical frameworks developed for studying this object establish methodologies that will guide investigation of the next cosmic messengers. The Vera Rubin Observatory's legacy. Survey of Space and Time, beginning operations in the late 2020s, expects to identify interstellar objects at rates of several per year. This dramatic increase in detection frequency will transform the field from rare opportunistic studies to systematic population analysis that can address fundamental questions about galactic material exchange. Enhanced detection capabilities will provide years rather than months of advance warning for future interstellar visitors, enabling dedicated spacecraft missions and comprehensive observation campaigns. The European Space Agency's Comet Interceptor mission represents one example of rapid response capabilities being developed for studying newly discovered objects. As 3I/ATLAS continues its ancient journey back to the stars, carrying with it the electromagnetic echoes of our young civilization, we find ourselves fundamentally changed by this encounter. This single cosmic wanderer has compressed billions of years of galactic evolution into a concentrated experience that connects us directly to processes operating throughout our vast cosmic neighborhood. The questions it has raised will guide astronomical research for decades to come, while the wonder it has inspired reminds us that we inhabit a universe filled with mysteries waiting patiently to be discovered. In studying this remarkable visitor, we have touched the deep currents of galactic evolution that connect us to the ancient stellar nurseries where the very elements of our existence were forged. Perhaps that's the most profound gift 3I/ATLAS offers us. Not definitive answers about the nature of interstellar visitors, but a humbling recognition that we are participants in cosmic processes far grander than our individual lives or even our species' existence. The universe has delivered to our telescopes a messenger from distant shores of space and time. And in receiving its message, we have discovered something extraordinary about our cosmic citizenship in a galaxy alive with endless possibility for discovery.